So now that we've kind of connected probability, to statistics, right? Or we've introduced probability from the numerical perspective, right? And the definitions, let's connect it to statistics, right? And so we start to talk about this term distribution again. And what that is similar to the distribution we've talked about in the past, right? It's every possible outcome of a random event, though, because of the random event process. Relative frequency, right, is, again, we calculate how often we expect that event to occur. And so looking at the outcomes of rolling a die, right? Here is the distribution. You can have outcomes 1 through 6 and then the probability. So when we talk about probability distribution, we're looking at this frequency or this relative frequency table here, right, as we look at that. And something we need to know as we do these distributions is that the sum of all outcomes has to equal 1, which is 100%. If you think about that, that makes sense. So to be a distribution has to represent all possible outcomes, and if you do that, then it will equal sum up to 100%. And of course, probabilities are always a positive value, right? In our context here. Continue on of other probability distributions. Here again, some sample situations. You can see my calculations here for them. And so looking at again, these simple probability situations, simple meaning that we don't have these complex events occurring, right? What are the probability of choosing a blue marble, red marble, yellow marble, and so forth? Here, again, here's an example of something that's not a probability distribution because these outcomes, something's wrong here, something's up, right? And those probabilities do not equal, they equal more than 100%, right? More than 1. And then again, you can't have a negative probability. So if you're speaking in that language there, you'll recognize that maybe something's up, right, in terms of negative probabilities, or it's more than 100%. You can't have that. The probability of an event of all the outcomes is between 0 and 1, including 1. I forgot to mention here, this here is called a uniform distribution because it's the same values, the same possible, the likelihood for each outcome is the same. Something to be mindful of. Some other terminology here. Many times the statistical thinking, we look at something called the complement, right? And so if you look at the notation, looks confusing, but all a complement is the leftover portion of a percent. So an example of I think in class when I did this, I used a salsa situation, right? What's the if there's a 20% chance that people like green salsa, what's the probability that they like another salsa, right, other than green, right? It would be 1 minus 20%. It's kind of the leftover of the 100%. So it's a form of thinking we use to solve some problems. And so looking at the notation is sometimes confusing. You'll see A with a C on top or A with a line across the top. It's called the complement. And so we look here to see how we solve that problem, a problem like that, right? If enjoying math is event A, right, does not enjoy math is the complement to that, right? It's everything left over. And so to get the probability of the complement, right, it's 1 minus 15 over 50. Again, this is a simple example to look at here, but you see 1 minus. You can solve problems that way if you think about complementary events. Looking at the probability of flipping a coin, getting a 3 heads in a row. This is the sample space here. If you flip a coin, and so then you can then answer these questions here based off of this here. So take a look at all the possible outcomes of flipping, right? And order does matter in this case. And so now that you've looked at that, we then have a rule that we use, a formula to solve what's called at least one situations, probabilities. What's the probability of not getting 3 heads in a row, right? Well, looking at what we have, our distribution here, you see it's 7 out of 8, right? Because there's 7 of them that do not have heads out of 8. Another way we could have solved that, right, is through this at least one rule, and said the probability of at least one no right heads is the probability of at least one tails, right? That language is equivalent. So I just want to make sure you understand that language, how the equivalent of the probability of not getting any heads is the same thing as the probability of at least one tails. They're related in complementary ways, and so you want to make sure you understand that connection, because many times once you make your interpretation, you can solve the problem using an at least one representation, using a complementary calculation. And then we end this one here with looking at the defining terms as unusual, and something is unusual if it has a less than 5% chance of happening. That's our kind of standard value we use. An event is unusual if it is extremely high or low from what we expect to see, right, the outcome. And so the number we use is 5%. Is it unusual if the outcome is less than 5%? We say it's unusual. Okay, and here's the example of the sample distribution of flipping a coin twice. What's the probability of getting 2 heads, 1 out of 4? That's not unusual. How about getting 10 heads in a row? The way that's calculated is, we'll learn more about this, is just multiplying 1/2 10 times. So it would be unusual if you flip 10 heads in a row. I'm going to finish real quick. I'm not going to explain these. I'm just going to show you the answers. You can scroll through that if you want to practice these problems here. And then we're done.